Next on the agenda, section 5.2. 5.2 is about right triangle trigonometry. So this is where we'll introduce our trig functions, sine, cosine, tangent, and the reciprocal functions. And what we're going to see is that those functions are based initially on right triangles. So let's talk super briefly about triangles and then what a right triangle is. And we'll look at one of their special properties, which is the Pythagorean theorem. So, triangles. Figure with 3 sides. And one of the properties is the interior angles add to 180 degrees. So all the angles on the inside, if I just sort of draw any triangle, the angles on the inside, kind of ABC, A plus B plus C, they're all going to add up to 180. If we were measuring in radians, well then they would add up to pi in radians. A right triangle is going to be a triangle where one of these interior angles is a right angle. And a right angle, of course, is a 90-degree angle. So 90 degrees, which is what we call a right angle, one of our corner angles. So what we get is some sort of generic triangle like this, right? And one of our corner angles, one of our interior angles is 90 degrees, is a right angle. We're going to mark right angles with this little box. Like so. And one of the things that we're going to do here is we're going to label our angles with capital letters. So generically we're going to use A and B and C. And one of the things is we're going to label the right angle. Again, not every single time, I guess, always and forever. But for the most part with right triangles, we're going to label the right angle as angle C. And then angle A and B, these two smaller angles, somewhat arbitrary, which is which. Depends on the setup. I guess my tendency probably is to put A sort of in the top and B here on the side, but even this picture you could sort of switch the orientation around a little bit, right? So the A and the B are kind of mobile, but the C we're going to use as our right angle. So C is 90 degrees, then that kind of means by default, right, if all three of these guys add up to 180, it must be the case that A and B would add up to 90, right? So that all of them in total add to 180. In a right triangle, one of the qualities that we're going to be particularly interested in is not as much based on the angles, but actually based on the side lengths. So we're going to use lowercase letters for the side lengths. And what we're going to do is we're going to sync those side lengths up to the angles that are across from them, the angles that are sort of opposite them. So angle A is up here, that means side A is going to be the one that's across. It sort of is across the triangle. B is here, so side B is going to be here, and that means the hypotenuse, which is our long side, is going to be side C over here. So that's across from the 90-degree angle. So side C is the long side. And it's what we're going to call the hypotenuse. A and B, we're going to be calling them the opposite and the adjacent, but it depends a little bit what our perspective is before we label those, so we can't just label those straight off the bat. So side C is our hypotenuse, that's going to be our long side, right? It's across from the 90-degree angle. There's a correspondence between the angle size and the length of the side that's across from it, so the bigger the angle, the bigger the side. They have sort of a linked relationship in that way. And so what happens here that's particularly nice in right triangles is they have this relationship with the side lengths where the sum of the squares of A and B are going to equal the square of C. Let's write this out. So this is our Pythagorean theorem. So this is in a right triangle. So this is not any triangle, right? I can't just draw a generic triangle and get this relationship. It has to be in a right triangle for sides A, B, C, where C is our hypotenuse. The relationship that we get is, so the sum of the squares of the short side, so that's A squared plus B squared, is equal to the square of the long side, is equal to the hypotenuse. So A squared plus B squared is C squared. This is sort of one of the math things that sort of once you've seen it, it's usually something people remember, even if they don't quite remember what it means. And so what this kind of allows us to do is if we know, not necessarily knowing the lengths of the angles, but if we know 2 of the 3 side lengths, we can kind of leverage that and find the third. What's going to happen to us is typically, not always, but typically, if we sort of pick numbers out of a hat, probably one of them, at least one of them will be a square root. This is a pretty particular relationship between these numbers. So there are some numbers where you can, some setups where all 3 of these will end up being whole numbers. A 3 and a 4 and a 5 here, for example, would work, or a 6 and 8 and a 10. Like a 5 and a 12 and a 13. There's a couple different sort of nice possibilities and sort of patterns that work. But in general, if we just pick numbers out of a hat, probably we're not going to get this pattern unless one of them is some sort of a square root. So let's do an example. So let's say, so if we have this triangle, I'll just do a sketch to kind of get us started. When we draw triangles, we're not necessarily trying to draw them perfectly to scale. We'll sort of do the best we can. So let's say this is a 2. Let's say this is a 4. That's kind of innocent enough, right? This is going to be our long side C. So what is the length of C? So the connection here, right, is 2 and 4 are going to be our lengths A and B. Again, we don't particularly care which is which. I just messed it up. Let's call that one B to be at least consistent with what I drew up top. Again, it doesn't matter. I would like to emphasize that again. It doesn't particularly matter. So if we set this up with our Pythagorean theorem, right, so our setup is going to be, so A squared plus B squared is C squared. So my A value here is 4, square it, plus my B value is 2, square it, equals C squared. So 4 squared is 16, plus 2 squared is 4. So that would be 20 is C squared. So if I know that 20 is the value for C squared, that must mean that the root of 20 would be the value for C. Now, 20 is a number that I could sort of break down, right? 20 would be 4 times 5, and this is useful because the root of 4 I can take. So that would be sort of root of 4 is 2 times the root of 5, which is just sort of left over. So if I take a square root of both sides, what I'll get is the root of 20, but then that would simplify down just with a little bit of arithmetic to 2 times the square root of 5. So if I know A and B, I can find C without too much trouble. We can kind of see it ends up with a square root here. That's fine, right? That's somewhat expected, just based on the fact that it's not always going to be the case that we have like perfect numbers that will like do this. Let me do another setup. Let me kind of change a little bit what this triangle looks like. That's not a very big change, right? This sort of angle is still down there in the corner. But let's say maybe now the long side is 4. And I don't know, maybe this is 3. So what would be this missing side? Would be sort of a in our kind of correspondence. So find the length of a. So same idea, right? A squared plus b squared is c squared. And then the orientation here, right? So my 4 is my value for c. My 3, the other short side here, is going to be b. So a squared plus b squared. So a squared is a squared, right? B is 3, so that's going to be b squared. This c is going to be 4. So a squared plus 9 is 16. So I'll do just a quick little subtraction, right? Subtract the 9 off of each side. So a squared would leave me with 7, and so that gives me a little bit of an easier root, right? Just the root of 7. Root of 7 is not going to reduce or simplify anymore, right? 7 is a prime, so it's not going to break down. So I'm content to just sort of get the root of 7, and that's going to be my final answer. So I can use Pythagorean theorem in a right triangle, not every triangle, right, but in this particular case, where if I know 2 of the side lengths, I can find the third side length. If you ever see people doing like survey work, or different sort of carpentry work or something like that, different construction work, you can kind of imagine where you would maybe have the measure for 2 different lengths and need to find this like long side, for example. Maybe this diagonal is something that you don't know as well. Or you could say something like you're trying to build stairs, and so maybe you're trying to hit a particular type of a slope, and you need to figure out, okay, so how long does the stair need to be and how tall does it need to be? So the Pythagorean theorem is going to sort of play a part in all of those different calculations. In any event, that's going to be our basis. What we're going to do next is take this right triangle picture and start to look a little bit more closely at the side lengths to get a definition going for our trig functions.